participants, as a source person for the session has joined us, Dr. Dwivedi from NIT Kurukshetra. And let me give a brief introduction about him to you all before starting the session. Dr. Dwivedi holds a PhD degree. He is currently an assistant professor of physics at the NIT Kurukshetra. He has been a postdoctoral fellow at the University of Sao Paulo, Brazil. In addition to being awarded the prestigious ISCA Young Scientist Award, he has been recognized with 4 other awards. Aside from holding 2 patents and publishing 24 research articles in international journals, he has authored 13 book chapters. He has been guest editor of 3 special issues in journals, Advanced. He has edited 3 research books. He has edited 3 research books: Synthesis, Characterization and Application of Multifunctional Materials, Spectroscopic Techniques for Security, Forensic and Environmental Applications, and Advances in Applied Spectroscopy. He has supervised 5 PhD students, 32 projects of Master in Technology students. He has been principal investigator of 2 research projects sponsored by DST and DRDO. He is General Secretary and Managing Editor of Laser and Spectroscopy Society of India. He is Executive Council member of Vigyan Bharati, Haryana. He has delivered 34 invited talks and participates in 65 international conferences also. He has international collaboration with several international academics like institutions in Brazil, France, UK, Ukraine, South Korea, and the USA. He has been member of advisory committee of several national and the international conferences. He was secretary and the convener of 7 international conferences and events. His research work focuses on the linear and the non-linear spectroscopic investigations of lanthanide doped materials for the development of random lasers, 3D nanofabrications by laser micromachining. So I heartily welcome you, sir, on the behalf of the organizing committee and personally myself in this ATAL FDP on the recent advances in nanoscience and nanotechnology. And the mic is over to you for the session.
Thank you, Dr. Sanjuji. It's indeed a matter of great pleasure to be part of this event. First of all, thanks to Honorable Vice Chancellor, Rajasthan Technical University, Deans, Head of the Department, and special thanks to organizing team, and further special thanks to Coordinator Dr. Sanjay Dwivedi for organizing this event and inviting me as well. I am really very happy to be part of this event. So let me share the screen and then let's talk. Hope you are able to see the screen.
Yes, sir, visible.
Okay, so it's now full screen. So
you can make it in the full mode.
It is already full mode. It's okay.
So we are seeing without full mode.
In full mode. So okay, let us rectify this first. I think it's full mode. So are you able to see the full mode?
No, not yet, sir.
No? Okay. I don't think what's the problem. To control because it's already full mode. So
in the present section, if it is asking for the present whole screen now, yes, sir. Now it is.
And now you can see. Okay, okay. So the title of my talk today is laser assisted fabrication of photonic structures for sensors. So several things are involved in this talk. First about laser, and then the photonic structures, and then the use of these photonic structures for as a sensor. So laser is a core of this photonic structure development technology. Laser invented in 1961, and up to now it is solely responsible for various optical events laser has changed the face of present scientific advancement and contribute a lot in day-to-day activities. In fact, there is no any other techniques, or you can say the scientific discoveries of 20th century that has been demonstrated with so many exciting applications. Now laser don't need any formal introduction to either science community or the common person in society. Everybody get interact with this word at least once in its lifetime. In fact, the development of lasers has been a turning point in the history of science and engineering. We not only use lasers as a diagnosis tool, but as a mechanical tool as well. So we can make several structure out of that, maybe 2-dimensional and 3-dimensional structures. This picture, you see the very beautiful butterfly, very tiny butterfly. This picture just to show that for what technology that we are intent to discuss today, that we can make various very small device, very fancy 3-dimensional device we can fabricate with the help of lasers. So this is the layout. Today's talk, I want to discuss at least 5 technology to you. First, the very brief about the photolithography, and because some of the aspect of photolithography that use with the help of lamps are being used in all 4 or 5 technologies. So I will discuss about that one. But since we are making photonic structures, so I will discuss about this photonic structures and some bit of laser and some applications of this as well. So at the very beginning, I would like to suggest some of the books. Those are very interesting formulas. You can find it, and fundamental physics behind the laser, the fabrication, and the application part as well. That you can see, you can find in these books. Like in case of the books, book written by S.N. Thakur. He has mentioned lots of formulas and the fundamental of plasma production and the surface texturing that you can see here. Very famous book, fundamental of lasers and related instrumentation you can find in Demtutor book. So they are some of the common books that people need to start work in this area. So we are talking about photonic structure. So just a brief 1 or 2 slides on photonic structure. So photonic structures are what? They are the periodic dielectrics, and they used to manipulate the light. So manipulate the light when we talk about, so it's not only control the intensity, the wavelength, it can also control the polarization, the phase of light, and all the related property it can change. So this is possible because it forms band gaps very similar to semiconductors that allow some of the light to pass through, or some of the light that should not pass through. So for this purpose we require different structures. Here you can see that structures are confined in nano dimension, in micro dimension, some mesoporous structures that may be distributed in 1 dimension, 2 dimension, 2.5 dimension, 3 dimension. Even the higher dimensions are also reported. Like 4 dimension. I mean, some of the example I will discuss here related to 4th dimension as well. So these structures are very complicated and very difficult to fabricate by the conventional techniques or the instruments that we have. So generally to develop a photonic structure, we have 2 approaches, very common approach. One is a top-down approach, and second one is the bottom-up approach, and laser is being used for both the purposes. So major technique that we have nowadays is lithography, patterning techniques, deposition technique, etching technique, and there are several subcategories are also there. So overall, if you break down this the category, so you will find 2 broad category, like top down and bottom up, or you can say the subtractive manufacturing technique or the additive manufacturing technique. So what these techniques are. So in case of subtractive techniques, we go through a material through various machining process. So, or it's better to use the word micro machining process. So usually we do this micro machining by CNC machines, or we can replace this drilling machine or cutting machine by laser as well, and we have some structures we can make it. But the result is we have lots of waste product. In case of additive manufacturing, we start with the very basic constraints of the material, and then we deposit one on one, and then we make a structure. So the basic difference between this product is the quality of the product, like what are the feature size, what is the shape, what is the finishing output, and further what is the mechanical properties and thermal properties of the material of the end product. So they are the the elements those help to distinguish this. But more importantly, if you want to make a very fine device, very fine structure, so it's better to go for additive manufacturing. So but if it is more than micrometer size or something, so you can use subtractive manufacturing. I will discuss this too as well in some of the example I will discuss with as well. So some of the major manufacturing or machining techniques are mechanical micro machining. However, they are the old one, and in that being used in CNCs very commonly they are being used. Chemical etching is another technique. Photolithography, LIGA that use X-ray and UV radiations, and then recently direct laser writing. Now it's a very developed technology right now. I will discuss in detail about this. And then electrical discharge machining. This is also very old one, where electrical discharge takes place through a needle while the substrate is dispersed in a dielectric solution, and then there you can have some structures. And then the imprint, lots of people are using this technique. And in addition to these, the major techniques, there are several other techniques are also there. But however, it's not possible to discuss every technique here. So just for the comparison point of view, we are comparing the micro machining techniques that we have. So you see here, we are trying to make comparison between the mechanical machining, like using tools like saw and drilling machines, the electrical discharge ADM, very famous uses machine technology that use in industry, chemical etch, and then LIGA. If you compare with this, the laser-based techniques like NDR laser-based technique, XIV based technique, or the tie-spire based technique, you see the distinction is very clear, that the resolution, the best resolution you can get if you are using the ultra fast laser, that fine structure you can grow which is less than a micrometer, and the surface fineness is also of the order of some nanometer. So however, no technique is best, and as per the need we can we should use this technique. So this is the comparison of some structure. This is the needle, steel needle, and that is cut by wire EDM, left hand side, electrical discharge machining. And here you see the surface is not very good, and some of the residual part is you can see here. But if you cut this needle with the help of laser, so structure is very fine and almost no residual is there. So this is the beauty of this technique, laser-based techniques. As I said, that the core of this technology, laser, play a very important role, and this saga of laser is very fascinating. Its stories related to its discovery is also very well known, and even several branch of spectroscopy and instrumentation, optoelectronics, it was not possible to invent even without the laser. So what are the basic characteristics laser have? Due to this, laser is being used for various purposes. The basic properties is like monochromaticity, directionality, intensity, and the basic reason of all these three properties, the coherency. So this is they are the at least four major properties, and that's why we are using laser not only as a diagnostic tool but as a mechanical tool as well. So just to take a glimpse of what is the size laser we have available. We have, so smallest laser so far reported is around just 44 nanometer. Just few molecules are come together and they laser. The biggest laser that we know up to now is 192 beams, laser beams that size of 3 football field size. So we have very small size laser and very big size laser as well. However, they are not serving the same purpose, and there may be some optical properties. Some of the properties of these photons are very same. The laser you can classify on the basis of several parameters, like laser power, the fixed frequency, or it may be tunable one, or the emission wavelength range. So laser is now we have laser that emitted in a deep UV region as well as deep IR region as well. Excitation source based correcting classification is also there. Laser may be continuous or pulse, and we can use both continuous laser and the pulse laser. Both we can use it for from photonic fabrication. I will discuss at least this portion in the talk. Further, the gain medium may be there. We have ion laser, we have atom laser, we have molecule laser, we have liquid lasers, we have solid state lasers, even the crystalline and the non-crystalline system. In all type of materials we have lasers. Just to summarize, till date we have very lasers with very fancy name, like free electron laser, Raman laser, X-ray laser, quantum cascade laser, another surface plasmon laser, digital laser that invented in 2012 in South Africa. Somebody report that you can generate any mode simply by giving a specific program to computer, so the alignment change and you can get a digital laser. This picture here, the article published in 2013 in Nature Communication. Now we have laser like random laser, the first invented in space. This is I think the only laser that lasing action that observed in space is a random lasing, and now you can get the lasing action in powder material, not the very well aligned specific materials. You can get this lasing action in powder material as well. So for biotagging purpose, for biological purposes, this type of lasers are very important. However, some application is yet to be reported. And then very interesting, the anti-lasers are also reported. Anti-laser report in 2012 again by Professor Cow team in USA. They make this anti-laser. So laser is supposed to give a very bright emission, but here this is the opposite case, where the laser is in this laser actually there is a complete destructive interference takes place. So like here you can see that the interference is complete destructive, and it acts like a saturable absorber, and no light is going to come out. So so there the application of anti-laser is yet to come, and but theoretically and experimentally now it is proven. So laser technology advanced so much, as I said, that you can just name a wavelength, and almost all wavelength laser available is available, and the power range is now people reaching to exawatt. Otherwise, till date the commercially available lasers of the order of 10 power 12 watt. We have a pulse width control around attosecond, 10 power minus 18 second, that width, and that is sufficient to monitor the every smallest or shortest event that is happening at atomic level in biology or chemistry that you can monitor. So we have a very fancy tool, and that's why that use for most of the purposes, for very small purpose, for to very big purpose, laser is being used. So, okay, let's start with the discussion on photolithography. Lithography, what lithography is? Lithography stands for two words, lithos and graphia. That means writing on a stone. So, of course, to writing on a stone is not an easy job, and people use different tools. So, here, in case of photolithography, we use photon as a tool to write. So on which substrate we can write? We can write a variety of substrates. Mostly in electronics, people use the silicon wafers. And to write the structures on that, we use a very specific material that called the photoresist. I will discuss all these basic aspects of photolithography here. Several steps are required for photolithography structures. To have a photolithography structures, first you should have to prepare a wafer. Suppose the silicon wafer you have, and there must be some contamination will be there, some body fluids or dust particles are there, so that we need to clean it, and there is a very specific procedures, standards are already reported. So we have to go through like RCA solutions we have to use to clean these contaminated wafers first, and then coat with the photoresist, and then pre-bake. That is what it called the soft bake is there, and then mask. Lithography can be done by masking or without masking. So this is the example of masking. I will discuss in detail about the mask, the photoresist, and everything. So several steps are required in case of photolithography, and every steps are very crucial to control the growth of a specific structure, size of a structure, the feature shape. These all steps are very crucial, and one has to be very careful about that. So start with photoresist. Usually we have two type of photoresist, even more than two type of photoresist are reported, but most commonly used are the positive photoresist or the negative photoresist. So in case of positive photoresist, that becomes soluble while exposed to light, so that's why it gives you the almost identical copy of the pattern that is printed on the mask. In case of negative photoresist, where the light exposed, that area is become insoluble or the hard one. So that means it gives you inverse copy of the pattern. So some basic chemistry need to know that how actually photoresist work. So several processes takes place when these photoresist exposed with photons of specific photons of energy and wavelength. So in case of photopolymeric photoresist or photo cross-linking resist, some free radicals generate, and that initiate the polymerization. In case of cross-linking, this cross-linking of chain takes place while it exposed with the light, and that's why that structure becomes so hard. But in case of positive photoresist, there is a photo decomposition that takes place as when the light fall on that material. So some hydrophilic products generate, and that help to dissolve that polymeric structure while expose it for a long time or adequate intensity. So this is the case of positive photoresist. Here you can say this no-lock, DQ, and ICA. They are the photoresist, and their absorption is well overlapped with this mercury arc lamp. That's why this is one of the best suited lamp. People use it for photolithography. Whenever we make a structure, so we have to take care of the. There must be sufficient amount of exposure should be there, like in in case of positive photoresist, exposure may be range of 50 to 150 millijoule. However, this depends on what type of material you are using and which wavelength you are using to actually expose with. So this is for the UV lamp, broadband UV lamp. So other materials like negative photoresist, we require much less energy, like 20 to 30 millijoule. However, for specific polymers like PMMA, if you work, so we require very high energy value so that structure becomes solid. So you can use positive or negative, both type of photoresist, but the key parameter is the what type of structure, what thickness of structure you want. So in case of positive, you can get around 500 nanometer minimum feature size, while in case of negative photoresist, there is around 2 micrometer. However, in some cases, people have reported even much lesser feature size, but that is require a very good quality instrumentation. Otherwise, you will not get that the fair, the edges and other things. You cannot get this. So theoretically talking, if you see, so if you want to make a structure like isolated lines or the island, so better to use the negative photoresist. So if you want to create some spaces or some specific contact in reverse of that, so if you want it, so it's better to use the positive resist. So there are some criteria is there, but however, you are free to use anyone depending upon your circuit design. So the efficiency of this photosensitizer or photoresist is very important. Like in case of DQ, diazo-naphthoquinone, this efficiency is only around 0.2 to 0.3, while in case of negative photoresist, this efficiency is at least 3 times more. So you have to select your photoresist as per the quantum efficiencies are reported. So some various resins are available in the market, commercially available. As per your structure you want or the lamps you have available, you can take that one. Sometimes to improve this quantum efficiency, we also use some additive so that additives don't destroy the property of the polymer, but it helps to absorb more photons, incident photons, and that's why we use some additive, however in a very small quantity for specific purposes. So one important aspect of this photolithography is the use of mask. Of course, some masking, some pattern is there, and replica of that or the identical structure of that is printed on this polymer. So these are the rubylith or the sodium halide coating on soda glasses, or it also on quartz substrate also you can see you can have this mask. So now the problem is the quality of this mask. If you see, if you have a mask, a plastic based mask, so of course the price is low, and that's why there is a low resolution as well. So but in case of quartz, if you talk about, we have a very good very high resolution. Of course the quartz is expensive as well. So if you, for a circuit design, if you want more than one mask, usually it require 10 or 20 or even more masks are required. So the cost of your circuit design is going to increase. In case of quartz, one very important feature is that you have a wavelength because it's a very transparent one, so you can use ultra UV radiation as well to 180 nanometer or even more. So the exposure, amount of exposure is very important in lithography. That way of exposure and amount of exposure. So there is at least 3 techniques is there. We have one is the contact one, second one is the proximity, and third one is the projection one. So what is in contact exposure technique? That the mask and the sample substrate both are actually in contact. So since they are in contact, so the mask may be damaged. Mask may be damaged, and you can use it for one time only. So this is old technique. Now people don't use it or use it for very restrictive applications purposes. In case of proximity printing, there is a gap between the mask and the surface or substrate. However, even this gap is leading to low resolution, which is of the order of some 1000 nanometer. However, in case of contact lithography exposure process, we have resolution even less than 500 nanometer. So a new technique comes in, what it called the projection technique, where the mask structure is projected through a lens or the mirror assembly on the substrate. So we have a much better control over the size and dimension of the the structure. So we have a resolution even better than 200 nanometer. However, further this projection system, projection lithography is also subdivided into three major sections, like scanning, step and repeat system, or in the hybrid system. So in case of scanning projection printing, we use mirrors to project one by one small image sizes just on the substrate, while in case of step and repeat, there is a expose of wafer, one rectangular section, what it called the image field, at a time we do this. So major difference is that since we are using lenses in step and repeat cameras, so we use lenses, while in case of scanning projection we use mirrors. So while we are using mirrors, so the size of mask and the printed size both are very similar, like 1:1. However, in case of step and repeat, we have either 1:1 or even 1:1 ratio to less proportion you can have. Third option is to we can use these two techniques simultaneously as well, like scanning projection and step and repeat cameras. Both we can use it, and we can somebody achieve this one the resolution around which is below 250 nanometer. So we can use it. So mostly we use a mercury lamp for this projection purpose, because of course very sharp lines are there. So this sharp lines helps to have a good contrast of structure. So they're the same thing. Here the photolithography process is a comparatively slow process. So if you want to make more structures quickly in a very a large amount, so we need to divide this beam, exposing beam, and then bifurcate this one, or even with the help of prism, or there are several other techniques are also there. So we can fabricate structures simultaneously for more than one substrate. So we can also manipulate the structure by using this using different type of lenses, cylindrical lenses or spherical lenses or other type of lenses. We can use it. I will discuss in later slides. So okay, and this is here. So this is the experimental setup, optics that are being used for XIV laser lithography. So here you see first we use aperture system, then the beam shaper. Beam shaper is a very important one, because if we want to tightly focus a light, so this diameter should be more. So usually laser dimension, the width, beam width is around 2 to 3 nanometer hardly. But if you don't use this beam shaper, so you will not get the very tight focusing. So for this purpose, we need to expand the beam, and further it need to be homogenized, because lenses what we use may not focus the light at one plane only. So there is some variation may be there. So for this we use very specific optical assembly that is called homogenizer. And then we use a field lens again to focus all these radiations at one plane, and some at different angularly variable optics are there inside this system, so that all the lights are going to focus at one point only. So and then we use mask and then projection projection lens, and then we put on surface. So this type of grayscale lithography, you can use it to make this type of structures. I think one example I'm going to share in upcoming slides. One very big problem in photolithography is the appearance of standing wave effect. What happened that the substrate reflects some of the light. So when the light is coming from in this direction from upward, and some of the portion is going to reflect back. So these two lights, incoming and outgoing reflected light, is going to interfere, and they form interference pattern. So that pattern, because your feature size is very small, so you are going to see these up and downs. The results you can see here. And this become very important when your feature size is very small. So we need to avoid this type of results in structure. So what we do, that we use anti-reflecting coating, or the absorbing, laser absorbing, or the radiation absorbing coating on the substrate, and then we design any particular circuit. So this is very important. Further, the problem is with the conventional lithography, that is mask based, is that these masks are, for example, the quartz masks are very expensive one, and I mean, for a very small site it's okay. For the big size circuit design, it is very expensive one, and to make one circuit, you may need several type of masks require. And there is no adaptability, that for one structure, if one structure is printed on mask, so it is for that purpose only. It cannot be for other purposes. And then the life of this mask depends on how you are going to use. So you require a clean room system, or otherwise one day they are going to destroy. So this is the problem with the mask lithography. So people start thinking about what are the other options to avoid the use of mask. So that's why a concept of direct laser writing comes in, and where the laser is directly focusing, so that on that part becomes solidify or soluble one. So in general, we have two techniques for maskless lithography. One is a rasterized one, or the vectorized one. So in case of rasterized, we directly we focus the image directly on the circuit, directly on the substrate, and that's why in case of rasterized, this image at the edge of that is not very clear. But in case of vectorized lithography process, we use direct laser writing by moving this laser beam by one, right? So the beam is used directly to write the image into the photoresist in form of one or more pixels at a time. So the edges you can see here in case of vector lithography process is very clean. So you can get very clean structures. So the same thing, this is the mask lithography technique, the way we use it. And here, if we don't use this, so we allow light to pass through some filters or some other process just to focus on a specific place where we want. So this is maskless and mask lithography. Further, there are other important lithography practice is a grayscale lithography practice. So what is this grayscale? Here you see this is a whole light is passing through this aperture. However, here there is some refractive index modulated structure is there, what it called reticles. So this is here, and due to this, only a specific portion is going to be solidified, and the structure you can see very different than this one, a lobe-like structure you can see. So the height gradient you can create with the help of grayscale lithography. Now we have lots of advancement in grayscale lithography, but due to the time constraint, I am just introducing the technology. Maybe next time or any other time I can discuss in detail. So now people are start thinking to use the mask lithography and DLW, that means the direct laser writing. Both techniques want to combine, or wherever it is used. So now people are not only just depend on one type of technique. It's better to use a combination of techniques to create one circuit. So let's go to the our major part, which is direct laser writing. Direct laser writing require a surface structuring. Maybe you are treating this laser or focusing laser on the surface only. You can also focus deep inside the substrate as well, like in case of glass substrate. So we say this is a machining process, laser machining process, because the structure size is in micro dimension. So we say this laser micro machining process. So why we want to use this laser machining process for the surface treatments? Because we have a much better control, we can control the heating of the amount of heat on the surface. So we can anneal the material, or we can help this material to undergo a phase transformation, so that it you can harden a small portion of material, or keep it less hard. So we can also melt a material to make alloying for cladding purpose, for grain refinement. So for different purposes we can use it. For vaporization, we can use this laser for it used for texturing, cleaning, thin film deposition, and further pinning is also we can do to hard any particular layer, steel surface, for example. So that all we can use it. However, a range of lasers are required for this purpose. So for micro machining point of view, we use much less power. Laser power is maybe of the order of 10 watt or even less than that. For typical annealing or welding or cutting process, we require a very kilowatt range laser. So why laser is need to be used for this type of treatment? Some additional advantages are there. For example, it is non-contact. That means you don't need to touch the surface or even the laser. So no tool is required literally that involve in this process of surface texturing. Further, almost no chemical is required, no etching is required, because the residual that is remaining on the surface is very small. Only with some air blow or nitrogen blow you can remove this, you can clean the surface. So the waste handling is very important here, especially when the feature size or the photonic structure is very small. Then it is become very important to clean the surface. So further, you can selectively remove the material or modify this material. For example, if it is a glass slide, let's say 2 mm thickness glass slide, so you can focus the laser on the surface or inside the glass slide as well. So I will show some of the examples that we did in our lab. Localized heating is there. That means if you want to confine, if you want to change the refractive index only within some micrometer dimension, that you can do. And while you are doing this, the other rest of the material is almost untouched, and it is there is no harm effect of high temperature that is there. So the under layers where you are focusing laser is almost without damage. Further, the flexibility of laser is we have. That means all type of laser powers you have, wavelength you have. So as per your material, you can select these lasers. So laser can be very fine focus within some order of a few tens of milliradians, and that's why to make a small structure we need lasers. So what happens when laser fall on a material? So it heat up the material, heat up the surface, and you see here the red portion here. So the material start melting, and the pressure inside the material is going to increase, and since outside the pressure is very less, so one day after sufficient heating, the explosion takes place, and due to this explosion some shock wave generated, and when this plasma cool off, you can see some structures here. So this is a very common methodology people use. So people use CW and pulse laser, both type of lasers for this purpose. However, in case of CW lasers, not very fine structure, you can get it. Only kilowatt lasers are required for this purpose, and for micro machining purpose we use a CW laser. Otherwise we use a pulse laser, and mostly we use a femtosecond laser, where the pulse width is of the order of 10⁻⁻15. So here this is one example that how it looks like when the laser fall on a material. So here you see only the heating or melting is there, that is almost without formation of plasma here. So two techniques again for direct laser writing. One is without mask, and with mask as well. So here this is the experimental setup. Some laser light is passing through beam expander. Of course, we want beam expander because we want to tightly focus this laser light. And then we have a motors X direction and Y direction. And where the substrate is positioned, there is another motor is there that is offering you the G direction. So we use a very common.
Sir, am I audible? Sir, you are muted. Just now you are muted.
Oh, okay. I'm sorry. I'm really sorry. How it maybe I wrongly clicked there. Okay, apologies for that. Okay, so I don't know for how long I was muted, but anyway. The most important part of this laser surface structuring is how much laser energy is required to ablate a material or vaporize a material. So with the help of this formula, you can you can estimate what is the minimum power density is required, and that formula indicate that this power density depends on the latent heat of the material and the thermal diffusivity of the material, or this density of the surface, density of the substrate. So there are several parameters are there, and that with the help of that you can estimate it. So but it is the minimum laser threshold is related to the wavelengths that you are using. So this is the one empirical formula. Here you can see the 600 multiplied to this annihilation energy, and which is divided by lambda square and atomic mass. So here you can see the laser threshold is reciprocal to the lambda. So that means what? If the higher the laser wavelength, lower will be the laser threshold intensity for the plasma breakdown. So the estimation, general estimation, is that if you require a gigawatt per centimeter square energy density for if you have a wavelength 500 nanometer. Otherwise, some megawatt energy is megawatt per centimeter square intensity is enough if you have a wavelength like 10.6 micron from CO2 laser. So for a specific material, you are going to see a specific power density requirement. For example, aluminum and potassium, you can see the least and the highest value of the threshold you can see here. For aluminum, we require more energy because the reflectivity of this material is very large. So another very important parameter for the surface structuring making photonic structures is the laser pulse width. So pulse laser may be of nanosecond pulse, picosecond pulse, or the femtosecond pulse, or even the microsecond pulse. You can see here, however, only few lasers are in microsecond range. Mostly people use either nanosecond or femtosecond pulses. So in case of nanosecond pulses, the dominant process for surface modification is thermal vaporization process, in which the simple material, when the laser focus on a material, so the temperature increases and then the phase transition takes place from solid to liquid, liquid to vapor, vapor to plasma, and further when it removed from the material, so some structure you can see. Now the problem is when the plasma form on the surface, the latter portion or the tail portion of this pulse are not going to be absorbed by the material, because plasma itself absorbs the major portion. So this is the unused energy we have. And further, the heat affected area in case of nanosecond pulse is quite large, and that's why the residual that remaining remaining of the surface structure is too much in comparison to femtosecond. In case of femtosecond and picosecond, the known both type of process takes place, like thermal bond breaking mechanism or the non-thermal bond breaking mechanism. In case of femtosecond, the most occurring process is the Coulomb explosion. So what happened in case of Coulomb explosion? You see, when the femtosecond laser fall on the substrate, so immediately it remove the surface electron, and that's why lots of free electrons are available on the surface when the plasma form. So, and underneath this layer, the positive holes are created, right? So that hole, those are created are, they are not going to escape, because the additional electron that transfer from one point to another point, it take around picosecond, and while within the femtosecond time, this the density of this electrons and the hole both are increases. So it become a very electrostatically very unstable situation, and that's why explosion takes place. So in this case of femtosecond laser, when hit the surface, so there is a Coulomb explosion takes place. This is not a conventional bond breaking system where the heating lead to the breaking of bond. Now the recently new techniques is now also reported, but it called the near field enhancement. Of course, this is the plasmonic effect, and you require nanoparticles you need to disperse in a solution. And due to the additional, this electric charge, due to the plasmonic vibration, we have this type of ablation. So mostly this Coulomb explosion and photothermal effects you can see while making the surface structuring by laser. So this is the pictorial representation of what I said, that while you use a nanosecond pulse, so width is too much, so only this portion, yellow portion, is going to be absorbed because this is above some laser threshold. However, this red portion is because its intensity is threshold intensity is less, so that's why it is not going to contribute to make surface structure, and it is also being absorbed by the plasma. So this radiations are not going to absorb by the material. But in case of femtosecond laser, here you can see that you see here that most of the light is confined in a very small pulse width, and that's why unused or wasted energy is very less. And here the heat affected area, you can see here, it's very less. So we have a less wastage of material as well. So how much will be the depth of material and ablation depth while we use femtosecond laser? So this formula is for femtosecond. So it depends on various parameters like F value, that is the laser fluence, R is the reflectivity, and this C is the specific heat. So if you know this parameter, so you can estimate the ablation depth. However, for nanosecond, there is another nanosecond laser. We have another formula is there. I will discuss in later slides. Ambient pressure is also very important. So if you are using this in a clean room or very specific ambient pressure condition, so it also changes the ablation rate, and that's why your structure is also going to change. One example here, if you use a nanosecond laser, so so you can see that if you are using the 100 shot, so structure is something like this one, while you are using 2400 shot, so it is much deeper here. But however, this structures outside the circumference of this, you can see that there are some residuals are there, so damage is more in case of nanosecond. So this is just for the comparison. Here somebody used this nanosecond laser, and here somebody used the picosecond laser, and this one is a femtosecond laser. So here the residual portion is very less in case of femtosecond laser, and nanosecond it is too much. This is the case in case of glass. We did here you can see this boarded glass, and you can see some residual are again redeposited near the surface. So now this become very difficult to clean. So some chemical again we require. So this is the formula that we use for the nanosecond purpose. So to estimate what is the depth of ablated crater. Again, the third very important parameter that affect the surface structuring is the repetition rate. So even if you are using the femtosecond laser, so femtosecond laser mostly comes in kilohertz region or in megahertz range. So in case of kilohertz range, what happened, the pulse separation is around 1 millisecond, while in case of megahertz it's only 12 nanosecond. So what happened that when one pulse fall on the surface, so another pulse come after 1 millisecond. So this time is sufficient to cool down the focal spot, and because this is the time that required to dispose the heat is around 1 microsecond or even more than that. So this is this refer to a breakdown mechanism where the one pulse is used to break down the structure. But if you are using the megahertz laser, so the again second pulse comes within the 12 nanosecond. So now the heat do not have a time to diffuse from the focal spot. So that's why the heat accumulation process is going to start here. So successive pulses start accumulating, and due to that a huge amount of heat develop at the focal spot. So cumulative process is responsible for in case of megahertz laser. So what type of structures or grooving you can do? This is the case of glasses that I did with the help of femtosecond laser. So we use 800 nanometer around very small power, and you can see here around 75 micrometer depth you can achieve here. Then we have variety of lasers starting from CO2 quasar laser to argon laser and other lasers. So variety of energy is available and wavelength are available. So this is up to you that what type of laser you want and which one is best suitable for your dimension or structure requirement. So again, the focal spot is one important parameter. However, you have much better control over that by using the specific laser and specific lenses and the wavelength. So for a particular structure, almost all the aspect of photon is playing an important role, like wavelength, focal length of the lenses that we are using, the energy, the pulse width, the repetition rate, all these things are required, and we use it. So overall, femtosecond lasers are best suited for this type of surface structuring, and most of the people use it. Talk about the experimental setup. Experimental setup is quite simple. The very basic setup is simple. Otherwise, lots of optics are involved here. So let us see here. So laser comes, reflect through mirrors, and then we use a filters assembly like energy attenuator to act as an energy attenuator, and then a beam homogenizer is required, and which is then light is focused, laser is focused through this focusing lenses, objectives, microscope objectives, and then fall on the one sample surface. So to see that where the structuring is happening, we need to use some very small camera here, and because some light is required, so we use a LED here. So now for the making structure in different dimensions, maybe X direction or Y direction, and then Z direction movement is required. So for this purpose, we use motors, mostly from Thor Labs. Otherwise, nowadays people are using the very fast steering mirrors that are voltage sensitive devices, and if you so according to the structure given to the steering mirror, this movement is happening. So this is the very small setup. You can see the laser is coming through this direction, and then beam homogenizer is here, and then we use a reflecting mirror here, and at this point is a microscope objective I use, and this is the camera. This is the microscope objective through which light is falling on the substrate. Backside of this, we use LED lights so that we can see where the structure is actually designing, and then this on the holder on which this you can see the aluminum block. This is connected with 3 motors for the transition in X, Y, and Z axes. So this is the microsecond. This is a femtosecond laser that is falling through a microscope objective. This is another experimental setup. Here in air, you can see the very bright blue color, and this is the glass slide, which is coated with some specific resin. And you can see here when this laser is very stable. You have to take care of that. If laser is not stable, your structure is not going to be very good. So we start focusing on the substrate here. Here you see the color is changing, and we make the structure of some 1 micron or hardly 2 enough 2 micron thickness that we do this. So what other work we can do with the help of these lasers is laser cleaning. This is the case. We attempt to make capacitor like structures. This is the gold coated mirror, and then we clean up the material and try to make these capacitors. We can make any dimension structures, we can make it. So what else we can make? We can make memory elements, waveguides, lenses, bulk and black gatings. Also we can do this. So mechanism process is that when we can focus laser on the surface or inside. So if the laser power is less, so only the refractive index modification is going to take place. Otherwise, if the intensity is more, so you may have plasma formation inside the glass slide, and some wide spaces is going to be formed. So 2 parameters that we have to take care of that. One is the beam size, and the rest of spacing. That means the spacing between the 2 beams. So that means the repetition rate that we have to take care of that. That is controlling the surface roughness and the feature size. So again, you have several parameters that you can play with. For example, the writing speed for the fixed fiber writing speed, you see with the different laser power, different line width and depth you can control. Similar to that, if you have a constant laser power and the different writing speed, so you can again have a very well control over the line width and the depth. In this both you can you have control. So to make gritting like surface gritting or the volume gritting, both you can develop here. We use 130 femtosecond laser emitting at 800 nanometer radiation. So you can may focus light inside at one particular plane, or even bit you can move this laser line, so you can make the, give this type of structures, layer on layer structure, and this may act like a micro lens. Maybe I think I have another slide to demonstrate this further. So very small gritting for one shot of femtosecond laser. Here you can see here do the constructive interference. Some is in these lines you can see. So this is the very small nano gritting you can say. So we use the the black coated glass slides to clean the surface. This is for the lab purpose. This is the Y junctions or the benzene ring kind of structure we fabricate within the glass slide. I think 1 mm glass slide was there, and around 100 micrometer in depth we make this type of Y junctions. We also make a memory element in praseodymium dope glasses, which is a green in color. So this blue strip you can see here, within that we make this type of the white spots where you are seeing. So that white spot is gives you a red color while exposed with the blue light. And if you expose this with the UV light, so this white spot is going to be finished. So also you can make a master mold with the help of femtosecond laser by simply engraving method. So you have one glass substrate and you can scratch it out some lines and then this type. So we use a polymer coated glass slide here that is doped with europium ion, and this type of structures you can see here. So advantage of that is you can control over the width of that, because you can confine the light, and here we are getting 2 to 3 nanometer only thickness of European emission. You can make microfibers. But the making microfibers within the glass slide or any glass slab, the problem is that when the laser start moving and focusing is there, so some spherical aberration takes place, and due to the nonlinear propagation, and the end point is never be circular. So you can see this is elongated at one particular dimension due to the depth of focus. So we make these structures at the end you can see here. So below the 100 micrometer, and we solve this problem by using the two cylindrical lenses system, and at the end you have a very fine fibers that are within the glass slide. 100. Yes, pardon? Pardon? Okay, so here you can see at the end again the very circular structures. You can see we connect light through these fibers as well, and maybe if you are able to see or not, some white spot here and here, there's the light that is passing through the fiber from one end to another end. So this is the diffraction pattern that's showing the very good quality fibers are there. So there may be one fiber, you can make it 2 fiber, 3 fiber, 4 fiber. So if you have a range of that, you can make a grating. So that grating is I make it, so this the dimension is around 2 mm, 2 mm or even less than that. So you can see that it is separating the color. We try to fabricate a different thickness of fibers. Here you can see when we connect it, the confocal microscope shows the white patches here, and that white patches shows some residual still is nearby this fiber. So these fibers are not very perfect. So we verify this change in refractive index of the material by the Raman technique. I have less time, so I will not discuss this one. We also fabricate this FBZ periods here to make a black grating. Okay, we come to laser stereo lithography. I think I will not discuss much about that because some portion is going to repeat. Only here in this stereolithography, stage is moving, stage is going upward or downward direction. So some solution is there. That solution is going to solidify under the laser power, and some structure you can see. So this is a different type of laser stereolithography is available now, and it is fall under additive manufacturing. So let's talk about multiphoton laser lithography. What is multiphoton? Multiphoton means addition of energy of one photon and more than one photons together to excite one energy state. So what happened that in case of one photon system, one photon is with the high energy is directly absorbed in one energy level. However, in case of multiphoton, for energy of one photon is not sufficient. So it excites the electron in some virtual energy state, and then from there again the re-excitation takes place, and due to these successive excitations, electron ultimately reach to my energy level system. So if you see here, this is the dye disperse material is there inside the qubit. When there is a one photon absorption takes place, so here you see the whole path is going to glow. But this is the case where we use infrared radiation, that means having the less energy. So where it is glowing only where the energy is highest. So that means the focal spot. So this is the overall mechanism of this multiphoton absorption lithography. In case of UV light, we cannot penetrate through the material. Most of the time it is absorbed on the surface. However, in case of IR radiation, we can, for deep focus, inside the material, we can deep focus the light. So what we do in this case, we select a material, monomer, and then photoinitiator that act in presence of suitable light energy, and then polymerization takes place. So what happened that when near the focus, the material is going to be solidified, and we can scan the laser in X, Y direction, and also in the Z direction as well. Of course, some optics are required, very similar that we have discussed previously. However, for better control, some other additional microscope objectives are required. All are not discussed. Maybe in the slide it is there. So the setup is very similar. So what is happening here? Laser is focusing in this liquidous material, jelly-like material here, and material is going to solidify through the process of two photon absorption, and then the additional material you removed it. So in this process, of course, no mask is required. However, to remove this resist, we have different chemicals. However, it is a bit difficult to remove negative photoresist. So sometimes we need to have plasma etching with the oxygen as well. Otherwise, with the positive resist, we can use simply a stone or trichloroethylene we can use to remove that. So what we can do with the help of multiphoton absorption lithography process is that such a complicated structures like dinosaur or spiders, we can make it. So this is good for nothing, but it shows the potential of your technology, that what type of structure you want, you can make it. Even the hanging spring type of structure, you can make it to catch a specific virus or a specific bacteria. For the filtration, you can make this cone type of structure. This type of photonic structures, you can make it with the help of two-photon to absorption process. Even you can dope some material to which act as a probe, that if there is some confinement effect is there, that you can see by adding a specific dye, transition, or lanthanide metals as well. You can make macro lenses. This is one example. Somebody make it of only 168 micrometer diameter. This is the lens. You can make group these lines, and these lines, when you scan on a glass material or a polymeric material, so some reflecting exchange takes place, and due to that this act like a lens, so you can make it with the help of femtosecond laser. Further, if you not only just one lens, you can make it if you have this type of structure. So when the light pass through at one time, you can make a series of micro lens array structures, what we call micro lens array. You can make it. You can give a just one experimental setup may be used for the very specific type of structures. Like here, this is the prism based structure where the light, femtosecond light, is passing through two mirror. However, one mirror is switchable one. That means we can change the angle of laser that is going through this prism. So at one specific condition, you get this type of pillars. But in another case, when you change the angle, so you will get this type of cross structure. So that these structures help to manipulate the light properties. Like one example of four-dimensional structuring, here you see different type of structure are fabricated by with the help of femtosecond laser. I think this is a negative resist are used here. So even the butterfly structure when it made, so you can see some colors are coming out, some filtration is going to take place with these colors. So let's femtosecond laser is very expensive one. We mostly it's very difficult for every lab to use it. So we have cheapest CW lasers available in the lab as well. How much time I have, Sanju, if you can? So
10 minutes more.
10 minutes. Okay, I have to be fast. Okay, so so for the CW laser, we mostly use the Lloyd interferometer. Here we have a cheapest, 505 or 550 nanometer laser that we pass through a special filter. We need this special filter, otherwise TEM00 mode is not going to come out, and then your structure is at the edges. The structure is not going to be good. So we have a mirror assembly here in this direction and in this direction, and then the sample is coating on this mirror. We can change the angle by rotating these stages, and then at an interference condition, you are going to see this type of laminar structures. You can make it. So this is the very simple representation that you have two mirrors, and your material is coated on one of the glass samples. But now, what will happen if you have another glass mirror here in the third side? So what happened in this interference pattern is also interfere by this incoming laser radiation, and then this structure destroy. The fringe structure is going to destroy, and it will destroy to convert in dot-like structure. And if you expose it for long, you can make pillars as well. So these are the structures you can create. So by using the different type of photoresist like SU8 or IPL, this type of structure, you can make like wood pile structure or spring-like structures. However, it is a function of how much light and how much laser power is there, and the stability of the structure. So mostly people use SU8. This is the most promising one. So application point of view, if you see for the anti-counterfeit, somebody made this barcode, the QR code, and within that QR code, some structures are there. You can write something that is very tiny. This is of the order of some 50 nanometer. So this you can write. So for someone is very difficult to replicate this one, and to authenticate the your machine, this QR code is required. So various micro optics elements, diffusers, micro lens arrays, gratings, all you can make with the help of this. Most important results now people are reporting is like to make photonic fiber bond because these circuits are very close, very compact one. So sometimes it is very difficult to have a connection between the two points. That now we can do with the help of femtosecond laser. And this laser, most of the time they are not a straight one. They are not the straight one, and you see some this wire bond can be make it. So just one technique I will discuss and then I will stop. So there are several laser based deposition techniques out there. Yes, yes, somebody is saying. Okay, so so we have several laser-based deposition technique like laser jet printing, laser sputtering, laser-induced forward transfer, laser-induced backward transfer. So now the most in the industry people want to use laser-induced forward transfer and the backward transfer, mostly forward transfer. What is that? So laser is falling through in this direction, and there is some transparent substrate is there that is not absorbing the laser radiation, and the bottom side of that some specific structure is there, or multiple coating is there, and that coating is directly you can plant on some deposit on some silicon substrate or wafer under the effect of very high energy of laser. So you can make this type of drops or donuts, this type of things, and of course this is a function of how much laser energy you are using. So you can make a 2-dimensional and 3-dimensional structure with the help of that one. So now this laser induced power transfer is very famous one, and a number of several branches are now is coming out. People have reported here. Mostly people use the dynamic release layer, where the sacrificial layer is deposited on the surface, and that help to release the one particular layer. There are several advantages are there. Because intact circuit or design you can directly implant on the surface, and some of the material where the laser cannot use to create a structure, that means the substrate is not going to absorb the laser radiation, then there we can use this technique. In case of metal films, this is we have very specific structures. For example, here the metal film is there, and when the laser pass through, so this become heat up, so it have take the shape of drop, and this drop you can catch on the substrate. In case of backward transfer, this is in reverse, because substrate is positioned here and the metal coating is here. So in reverse of that, the forward direction deposition, we have a reverse backward direction depositions as well. Major advantage is that you don't need a clean room. Most of the cases you don't need the clean room, or in general room you can, in the ambient atmosphere, you can create this, you can create these structures. So different type of not only 1-dimension structure, 2-dimension structure, 3-dimension structure you can create. For example, some of the example I would like to share. One like in this case, copper rod fabrication is there. One-on-one drop is falling through, and then you can collect to make one particular structure. Copper is already demonstrated. In case of LED, you can see here that laser is used to make some kind of cavity or grooves there inside, and then one specific structure which is pre-deposited on a surface, and that is depositing with the help of laser, so inside the cavity, and then the connections to make connections, we again use the laser and by using this forward transfer system. So making cavity, transferring a whole design layer design, and then making a wire. These all can be done with the help of laser. And here you can see this LEDs are also, this is performing one. So somebody used the lithium-ion macro batteries as well, where the different layers are deposited with the directly deposited with the help of this laser-induced power transfer. Laser-induced graphene is also one very important aspect. Under the very high laser light intensity, there is a carbonious material converted to graphene. And because time is less, so I will not discuss in detail. But so if you use a specific substrates, so you can create the graphene directly. You can write a graphene structure. So somebody use this very simple device on polyimide structure, polyimide substrate by using the CO2 laser, which is commercially very easily available. 1 watt laser is very easily available. It's a cheap one as well. So that use electrochemical analysis to detect the hydrazine. Similar to that, another demonstration people use to have use this type of laser-induced graphene structure to detect some biological markers for wine and detect this microRNA as well. So time is less, so I will not discuss in detail much. Somebody make this variable strain sensor. They use solution of graphene oxide and HAUCl4 solution, which is a gold source, and make a structure with the help of laser here, and that act as a variable strain sensor. Moreover, we can make interdisted this laser-induced graphene electrodes as well on a polyimide seed. And not only polyimide seed, we can use PDMS or PET seed as well. So somebody is already demonstrated. This is the case where people try to attempt some connect these devices with the Wi-Fi and to live monitoring the sulfate ions. So mostly people use up to now they have demonstrated this detection of hydrazine, sulfate ion, ammonia detection, uric acid detection, and this microRNA. These all can be detected with the help of laser-based system. So they are the applications I had already discussed. Okay, then thank you.
Yes, sir. Thank you so much. So participants, if you are having any query, you can ask to the expert directly, or either you can write down in the chat box.
I was too fast at the end because I think that I'm taking too much time.
So that was a wonderful session. Every detail you discussed about this, all the technique. So to the participants, you can ask your query to the expert.
The few techniques are very new. Few techniques are very new, and only few groups in India those are working in like laser-induced power transfer and backward transfer. However, probably start working, and industry is also taking care of that one. They to invest in these techniques. So at laboratory level, we need to optimize, and in Indian point of view, it is very important because only few labs are there. Even we are starting this thing. However, we are waiting for our laser, nanosecond laser. We are waiting for. Otherwise, we will also engage ourselves in this technology development.
Yes, sure. So, any participants?
So it's a lunchtime. It's difficult to ask questions.
No, sir. It's okay.
Anyway.
Yeah.
But I'm available. My email and my telephones are already available on the website of NIT. So anytime any student individually if want to discuss with me, I will be really very happy to share my experience with you all.
Yes, sir. We will provide your email and details to the participants in the when the final feedback will be sent to the participants. So surely they can contact you.
Yeah, sure.
Okay, sir. On the behalf of the organizing committee, I thank you for the wonderful session. And hopefully, in the near future, also we will meet in person whenever the conditions will be
Sure.
okay.
Sure, sure. It will be my pleasure.
Okay, sir. Thank you so much.
May I leave now or?
Yes, sir. You can.
Okay. Okay. Thank you.
Thank you. Thank you, sir. All the participants kindly join in the valedictory section at the 3 p.m. And the quiz, as informed on the group, will be posted at the 4 p.m. and you can complete it by the 8 p.m. So from 4 p.m. to 8 p.m. as per your convenience, you can perform the quiz. And please kindly come in the valedictory session at the 3 p.m. and give your feedback so that in the future we can improve our programs with your suggestions.